Okay, thank you very much. So I'm going to follow on, moving back a little bit more towards a materials theme, but with some topics in common with what's been discussed so far. Let me start off by motivating local chemistry both drives and is driven by long-range stress concentration. So these are examples of problems that we call chemomechanical systems, local chemistry and long-range mechanics, things like fracture, friction, and plasticity. And these are particularly challenging systems to model because we need accuracy locally. We need to describe breaking bonds at a crack tip or the rearrangement of the core of a dislocation, but we also need large model systems that typically take us well beyond what can be done with a standalone density functional theory approach. So of the order of 10 to the 5 or 10 to the 6 atoms typically, to avoid putting the boundaries too close to the system of interest and affecting the results of the calculation. Okay, so this is the kind of standard hierarchy. The first idea would be to try to use existing empirical potentials. Before moving on to how we've been constructing machine learning approaches, I just want to motivate some of the drawbacks of existing interatomic potentials, and in particular the challenge of not knowing what the domain of transferability of a given interatomic potential is. So how to know when you can trust it and when you can't. So here's a typical materials science example. I'm doing a molecular dynamics simulation here of dislocation glide in a model of a superalloy. So this is a nickel system with a little bit of aluminium, an otherwise very good interatomic potential, an embedded atom model by Yuri Mishin, which is doing a great job of describing the bulk and elastic properties of the material. This is at a reasonable temperature, and we see these dislocations whizzing around nicely. So this is a dissociated screw dislocation in a piece of nickel gliding around at room temperature. And one might be very tempted to take numbers out of these kind of calculations and use them to try to make larger scale, mesoscale models and really make predictions. And the question is, how far can we trust the transferability of this approach? So how accurate in particular is the description of the separation of the two halves of the partial dislocation? And what if we want to put extra chemical complexity in? So where does the interatomic potential framework stop? Where can we no longer describe things using simple interatomic potentials that we can train on ab initio data? So actually, it may be even sooner than you think. So for this relatively simple system, we're actually making quite a fundamental error. So if we look in a little bit more detail at what's going on in a post-mortem of this simulation, if we start up here, the embedded atom potential was actually fit to describe the stacking fault. So the energy associated with creating a stacking fault is perfectly reproduced. Both the unstable stacking fault and the intrinsic stacking fault energies match up very nicely with DFT results that are shown here in blue. However, while the matrix phase, the FCC nickel matrix, has its elastic properties very well described by the potential, again, that was included in the fitting set. So the things that I've shown here in green were included when training this particular traditional interatomic potential. The HCP phase was not trained. It wasn't thought that that was particularly important because nickel doesn't sit in HCP. However, the stacking fault that links the two halves of the partial dislocation is rather reminiscent of HCP. So by getting the elastic properties of this phase wrong, this particular potential dramatically underestimates the separation distance of the two halves of a partial dislocation. And if you think about the relevance of that for processes like climb, where the two halves of the dislocation need to come together before it can take a step up, you're going to get an exponential error in the rates of those kinds of processes. So this is a very simple example of a potential that's otherwise very good, falling down when you move just a little bit outside of the range of where it's been calibrated. And if we want to understand why this potential is failing, we can delve into it in a little bit more detail. So this is an embedded atom model. It consists of two contributions. There's an embedding term that describes the effects of electronic embedding. And actually, that's very similar between the two phases. That's unsurprising. The electronic structure of the nickel atoms in both phases is actually rather similar. And then there's this pair term, which has to mop up everything else. And that's what's failing to give us the transferability that we need here. So once you've identified this problem with this particular class of potential, you could go beyond the pair potential. You could move from an embedded atom model to a modified embedded atom model, put some angle dependence, generally extend the number of parameters in the potential and take it a little bit further. But until you know you've got a problem, there's no way to anticipate this lack of transferability. Okay, so that's just an example of the kinds of things we'd like to be able to do. Of course, it would be nice to simply do density functional theory, which for many systems is sufficiently accurate and transferable. Of course, we're limited in terms of the size of systems that we can address, and in particular, the timescales that we can address. And I think that's really the most important case for using machine learning approaches in this domain. It's really to extend the timescale, as I'll show later on. Just one example of where you can make useful predictions with a density functional theory approach, even in what appears to be a large system, where you can compute appropriate quantities in small periodic systems, then you can really try to make quantitative predictions that can be compared with experiments. This was something we did very recently on the fracture toughness of silicon carbide. So there, my collaborators at Imperial were able to do fantastic single crystal experiments. So using a cantilever system like this, driving a wedge into a single crystal of silicon carbide, they could measure the fracture energy, and we could actually do DFT calculations of the surface energy just in small periodic cells. And we get reasonably good agreement, especially in comparison to previous experiments which weren't able to get down to that scale. But that's really a sort of special case. We'd often like to be able to model very much larger systems for very much longer times. So the approach I've been involved in for quite a few years, and what's really inspired the more recent machine learning work, is a concurrent approach where we couple a density functional theory description of small parts of the system with a classical description of a much larger system for an embedding scheme. So I just want to very briefly give you an example of that, because as I say, it's really what led up the development of the on-the-fly forced learning approach I'm going to talk about in a second. Okay, so this is the learn on the fly scheme, as it was called at the time. Perhaps learn wasn't the best choice of term. Actually, it's more of a fitting approach, and it's only recently that a more machine learning approach has been incorporated within this framework. But the basic idea is that we've got a large part of the system which is not doing anything terribly interesting and can therefore be described by a relatively simple model. So these million or so atoms far away are pretty much within the harmonic regime, or certainly can be described by an interatomic potential, not necessarily a pair potential. And there's only a few atoms that are doing something interesting. They can be treated with a higher level approach, in this case density functional theory. This particular approach allows a dynamic changing of the region that we treat with high precision, and that's because everything is combined at the level of forces. And that's actually the inspiration for the machine learning approach here. So the idea is that if we get the right forces in all the atoms, then we'll follow the correct trajectories, and we can actually reconstruct appropriate free energy differences between configurations. Even though we lack a single potential, we don't have a Hamiltonian of which these forces are the derivatives. If we get the right forces everywhere, we should follow the right trajectories and see features of interest. Okay, and the advantage of this particular approach is that we can put whatever chemical complexity we like into this quantum region without having to do any reparameterization. And I think that's why QMMM approaches like this have stuck around over the last few years, despite the advent of machine learning approaches, because we can really increase the chemical complexity for a fixed cost in this localized region. We can look at a number of applications. So I just want to mention some of them very briefly because it really introduces the case for moving towards a machine learning approach. So initially we did things that could be done within a DFT time scale on the sort of 10 picosecond or so scale. You see something happen, something catastrophic, interaction between cracks and defects, or scattering from dislocations. And then more recently we looked at some very slow processes like stress corrosion cracking, so where you see cracks that start to grow in the presence of oxygen or water. However, again, the individual chemical reactions happen on a DFT timescale, so you can see something in the 10 picoseconds that you can afford to simulate. It's only when we've started to try to access this thermally activated regime in the middle, where you would need to run simulations in principle for hundreds of picoseconds or nanoseconds, that we've really gone beyond the capabilities of what you can do with a multi-scale coupled quantum classical scheme. So QMMM and things like that really help a lot with length scale problems. We can really get beyond the limitations of DFT in terms of the number of atoms we can address, but they don't help a great deal with time scale. Actually, even from the beginning, we had a kind of time acceleration scheme incorporated within the approach through a predictor-corrector style setup. So if you watch these kind of animations enough times, you see that they're rather repetitive. The same things are happening again and again, and it seems kind of stupid to do DFT force evaluations at every single time step. You really should be trying to encapsulate the information that you encounter and reuse it as efficiently as possible. So what was done initially was a rather simplistic fitting approach, essentially, where we calibrate a simple model which consists of the underlying classical interatomic potential plus some correction. And that correction is adjusted every few time steps to reproduce the reference quantum mechanical forces. So one of these fit points here, we do a DFT calculation, we fit these constants alpha, and we go on for a few time steps, extrapolating with fixed parameters. As we extrapolate, the error that we incur in the forces increases roughly linearly with time, so we can set a threshold for the maximum force error that we're willing to tolerate before we go back. We don't actually incur this error in the final dynamics because of this corrector phase, so we do a subsequent fit at the end of the extrapolation cycle. We have a new set of parameters, and we go back and repeat that segment of the dynamics, interpolating the parameters that are valid at the two ends of the cycle. Okay, so this was really the inspiration for the on-the-fly force learning approach that I'm now going to describe, and it's a complementary approach to what Gabor and Anatol have been talking about earlier on, which is based more on trying to build a picture of the potential energy landscape. So here instead, rather than trying to learn the entire potential energy landscape or an appropriate subset of it once and for all, we're going to use the same kinds of technology, so Gaussian process regression in this case, to try and learn the quantum mechanical forces themselves as a function of the local environment surrounding a particular atom. And the idea is that keeping in touch with the quantum mechanics should reduce the chance of extrapolating too far outside the domain of applicability of the approach, so to try and alleviate the concerns that I raised in the example at the beginning with the superalloy. Okay, so this is a kind of diagrammatic representation of what's envisaged here. So we go along doing our dynamics, and we want to accelerate the scheme overall by whenever we have a new configuration for which we need a force in order to advance the dynamics, we look in our database of configurations that we've encountered so far, and if we have a sufficiently accurate representation of a similar environment, then we can predict the force using Gaussian process regression, or if the predicted error based on the existing database exceeds some threshold, we can automatically trigger a new DFT calculation, augment the database, and carry on from there. Okay, and databases were initially envisaged as being trajectories, so per project, but of course they could also be shared between projects, or indeed using a repository such as Nomad to make the kind of bootstrapping potential available to a wider community. Okay, I don't think I need to say too much about Gaussian process regression. This has been well covered earlier on. Suffice to say, we are doing some regularization. So we are including an estimate of the assumed error on the input forces with which we're training. In this case, we're typically training from clusters, so from DFT calculations carried out on clusters, and that means that there is an error associated with the forces that we take compared to a full periodic calculation just from the truncation in the cluster. So we have an idea for what to put in for this data input hyperparameter. We're using a Gaussian kernel, a squared exponential kernel, and then the usual estimates for the posterior mean and the variance. The challenge of this scheme is that we're trying to predict vector quantities, forces, rather than scalar quantities such as local energies or total energies. So we need to come up with a fingerprint, a representation that describes the similarity of two configurations for the particular case of learning forces, learning vector quantities. And what we did as a first approach a couple of years ago, and actually this has been built on by Sandra De Vita and others since then, and I'll say a little bit about their recent work and some of the applications that I've been involved in that use it in a minute. But what we did initially, as a kind of proof of principle, was to construct a set of vectors running from an atom to all of its neighbors, and then use those to produce an internal vector representation, as shown here. And these vectors can then be combined to construct what we call a feature matrix, or a description of the local environment. And the advantage of doing it in this way is that we transform the force from the original Cartesian coordinates into this internal vector representation, and then we have a scheme which is covariant with respect to rotation. So if we rotate the configuration, the force gets rotated as well, and that means we can learn in a way that's invariant to rotations. Okay, and then we use a distance metric, which is just a function of the features of a particular configuration and the other configuration of interest. Okay, how does it work? So the first thing to test is one of these standard learning curves where we're adding training data and looking at how the accuracy of the predicted forces improves. So using just this internal vector representation, we do see a kind of saturation at errors that probably are too large to be considered acceptable. But a nice thing about this approach is that we can benefit from all of the hard work that's been done over the last few decades to construct robust interatomic potentials to augment our descriptor with additional force vectors that carry information about the configuration. So we're not assuming that the forces that come from, for example, an interatomic potential or a type binding representation are themselves proportional to the DFT force, but they carry information that correlates with it. So by augmenting our feature set with forces that come from other Hamiltonians, you can see we significantly improve both the rate of learning and the point at which we plateau. This plateau is associated with not really carrying all of the information about the environment. So there's a lack of completeness in this descriptor, and that suggests there are ways to improve here. However, we do get within a few percent of the DFT forces with a few hundred configurations. So by selecting the 500 most relevant configurations, we can get a 6% error with respect to DFT forces. This is in 1,000 Kelvin silicon, so a reasonably tricky set of environments to learn. Now we can use it to do dynamics, so moving from a test to one where we're really doing on-the-fly dynamics. If we start, first of all, at a relatively low temperature of 200 Kelvin, when things are just bouncing around in the bottom of mostly harmonic wells, this is the red curve here, we actually see we can go for really, really long time periods without the requirement to call on the DFT Hamiltonian at all. So these blobs here represent individual configurations. After the first picosecond, when we have had to do quite a few things to build up our initial database, we can actually run for more than 1,000 time steps before needing any additional quantum information. And we run on a little bit longer, we need a little further burst of activity. However, you can see that there's still work to be done in the quality of the descriptor that we're using, because when you move up from 200 Kelvin to 1,000, we no longer manage to run forever. We instead get a cadence of about 1 in 30. So every 30 steps or so, we need a bit more information from the DFT. Still, that's a speed-up factor of 30 compared to doing a standard calculation, which compares well with the speed-ups of about 10 that we got with a more straightforward predictor-corrector scheme, where we were just fitting a simple model, using it for a while, and then throwing it away. So we are encoding some information which comes back into being useful a long time after it was first seen. Okay, and there's another demonstration that I can show of that. So this is a test system which has moved from a low temperature regime of about 300 Kelvin to a higher temperature regime of 800 Kelvin over a number of cycles. And this is really a demonstration that learning is taking place over a longer time period. So what I'm showing at the bottom here with the red stars is each individual DFT calculation is a red star, and the blue histograms just count up the stars associated with each of those temperature windows. Okay? So you can see that the first time we hit a high temperature regime, everything's a bit unexpected. The system has to trigger a large number of high accuracy calculations, DFT calculations. But the next time we come around, we don't actually need as many. And in particular, when we return to the low temperature environment, we've seen everything that comes up, and we don't need any further configurations to enter the database at all to describe the 300K environment. As time goes on, we need fewer and fewer configurations, at the high temperature environment until this point, 30 picoseconds into the simulation, when something new happens and we have to trigger a burst of additional influx of quantum information. You can see a little spike in the temperature here. What actually happened is that two atoms got rather close together and generated a new kind of environment that hadn't previously been encountered. So even at 800 Kelvin, it's hot enough to do things that hadn't been encountered in the training set up until then. So this is, again, an indication about the kinds of considerations one has to take into account when using fixed interatomic potentials, so the kinds of tests that should be envisaged. Right, so that's pure silicon. Recent work has been done to extend both the way in which the features are described, so I wasn't directly involved in that. You can read about the details in this paper that came out in PRB, and then it's been applied to some more metallic systems. I have been involved in that part. One of the tutorials you'll be looking at after the coffee break is actually using this approach directly, so I won't say too much about it now. You can read more about it in the notebook that accompanies the tutorial session, which Gabor will introduce in a minute. But essentially the idea is to use a matrix-valued covariance, so rather than throwing away the information that's carried by the vector nature of the forces, build that explicitly into the covariance between configurations. So the correlation between forces on two different configurations can directly be embodied in a matrix kernel. And then we do the usual Gaussian process regression for a vector using a matrix kernel and the coefficients that come in the usual way from the Gaussian process regression framework. Right, how does it work? Well, if we have a look at this iron example, you can see that the bulk configuration is very much more accurate than the one containing defects. That's not terribly surprising. But what's interesting is that with relatively modest numbers of training points, we can get to an acceptable force accuracy, even when we have defect environments around. So the horizontal lines here show the average force errors incurred by interatomic potentials, EAM models that are widely used in these materials. So with only a few hundred training points, we're doing quite a lot better than EAMs for comparable computational costs, the same scaling at least. If we look at the performance in bulk nickel and in bulk iron compared to the embedded atom model, so the ML scheme is shown in red. The red points are clustered more tightly to the diagonal line, showing a perfect correlation between training and predicted forces. And in particular, at large amplitudes of the force, you can see that the blue EAM is deviating more significantly from the perfect prediction. So it looks like it's working reasonably well. There's more work to be done in terms of applications, but I think it's quite a promising approach, and it's complementary to the work that's being done by Gabor and others on potentials. I think there's room for both approaches. Okay, just one last point I'd like to make to forestall common criticism that we've given up the idea of having a total energy function. We've just got forces. Is that a problem? Can we still reconstruct important things such as energy barriers between configurations? So my claim earlier on was that if we get all the forces right, then we are describing the correct trajectories, and therefore we're not incurring fundamental errors. I've been doing some work recently to try and use that idea to reconstruct energy barriers. So to start with, just zero temperature potential energy barriers, but it's very much the same idea as thermodynamic integration, so it could easily be extended to free energy barriers at finite temperature. And that's just by integrating forces between a pair of configurations in order to recover the energy difference. So if we have the forces exactly right, if they did come from a Hamiltonian and then we were to integrate, then clearly we would reconstruct energy differences and we could get energy barriers. We haven't tested this with the machine learning scheme yet, but I want to show you some results using this approach with the multi-scale, so the hybrid scheme where I've got forces from one Hamiltonian in one part of the system from DFT and from a classical model in the other part of the system. We've been careful about matching the elastic properties between the two parts so that we don't have inconsistencies. But there could still be problems because of doing work in closed loops. So the first example was something where we already know the answer, where we can do the reference DFT calculation using a total energy scheme, and that's vacancy diffusion in FCC aluminium. So here, you can see that this approach of using only a very small cluster centered on the vacancy, I think only 15 atoms or so around the vacancy, and combining that with an embedded atom approach and using force integration, reproduces the energy profile very well for a fraction of the computational cost of the full DFT calculation. So that's just a validation. We then moved on to something where we weren't able to do the reference calculation, and that's the case of the diffusion of an edge dislocation in BCC molybdenum. And there, the best available potential estimates an incredibly high energy barrier in comparison to what we find when we use the QMMM scheme to estimate forces. And you can see that we get systematic convergence with respect to the cost of the embedding scheme. So we have this buffer that surrounds the quantum cluster. We make that bigger and bigger to improve the quality of the forces that we're using in the core of the quantum region. As we make that larger and larger, up to around 10 or 12 angstrom, we can converge the height of these energy barriers within 0.01 eV or so. So I think that similar approaches could be used with forces that are coming out of machine learning schemes to demonstrate that it's possible to reconstruct energy differences and energy barriers using those approaches. Right, so just a bit of outlook from me. I've shown that we need, in order to study these kinds of systems, the ability to cope with complex chemistry, so not just single atomic species or even two. We might need 3 or 4 atomic species, and it's great to see people pushing in that direction. We also need to be able to address long timescales. I think the machine learning approaches help a lot with that. We can start to push to picoseconds and nanoseconds, large numbers of picoseconds and nanoseconds. But something else that I think is important is to be able to quantify the uncertainty arising from the predictions that we make. And I think that's really one of the next frontiers that we need to address. That's actually something that the center of which I'm a part in Warwick, the Warwick Center for Predictive Modeling, is focusing on in particular. So we've got projects across the length scales aiming to quantify errors that arise from the results of approximations that we make when we do calculations. I think this is something that was covered a little bit in yesterday's tutorial, error bars on quantity. So I just want to give very briefly my perspective on this lower end part, so how to quantify uncertainties in exchange correlation functionals. It's some work that we've done recently, which is again complementary to the Bayesian error estimation BEEF. What's the F stand for? Framework? Not sure. Approach from DTU in Copenhagen. And this is a slightly different approach. It's a fully Bayesian approach. We start from the same point, so we take exact correlation energy, but we write down the exchange energy as a sum of coefficients times Legendre polynomial basis set as an enhancement factor over the uniform electron gas. And then what we do is we assume that the observed data, which in this case comes from experimental atomization energies, follows our proposed model on average, but with Gaussian noise. And that means we can actually infer, rather than a point estimate for these coefficients, a full posterior distribution, so a full probability distribution for these coefficients. And that means we get a full posterior distribution for the exchange enhancements factor, and we can propagate that through the DFT code so that we can actually get error bars on quantities of interest that come out of the code. So I've just shown a few examples here. We can essentially sample from this ensemble because we have a full analytic representation of the posterior probability distribution associated with the exchange energy, the one of the two unknown things going into DFT. As I say, we haven't done correlation yet. We can sample from that, and we can get things like the bulk modulus of carbon is 500 GPa plus or minus 50, and that plus or minus 50 is just coming from uncertainties associated with the exchange energy. So that it helps to give a bit of confidence in what the errors associated with the approximations that we're making in DFT are. Okay, I'm being waved at, so it's time to wrap up. So I'll just finish with acknowledgements from all the collaborators in Warwick, King's, the Technion, Cambridge, and elsewhere, funding and computers. Thank you.